Section 2.2, the limit of a function. Our main objective in this section is to really just introduce the idea of a limit. We've kind of mentioned that previously as far as what a kind of the idea of what a limit is, but we want to go ahead and clarify exactly what do we mean by a limit. What does a limit describe? How do we evaluate a limit, and at least in the general sense. Now, at this point, keep in mind, you always got to walk before you can run. Uh, there's going to be a lot of grunt work, I call it, at this point. A lot of crunching of numbers and using the calculator to do a lot of calculations for us. So you have to remember we're kind of at the beginning of this discussion. So we'll talk about this basic idea of a limit and how do we evaluate limits. But eventually we'll look at you know quicker and easier ways to do this. Right? So this is kind of, I always call this is your paying your dues part, of course, where you kind of have to grind your way through some of these basic calculations. But keep in mind it will get a little bit easier, and the process will be a lot more streamlined going forward. Right? So keep that in mind. But this does absolutely help to understand. Later when we have discussions about limits and like as I mentioned, derivatives before, understanding what those are and what it is that you're evaluating. This goes a long way into making sure that we have a clear understanding of exactly what those concepts are all about. All right. So the limit of a function, our main kind of notation or terminology that we use. We say that the limit of f of x as x approaches a is L. Now again, I want to be clear on the different parts of this statement. So the limit as x approaches a. What is a? A is a specific x value, right? So like if you think back to the examples that we did in the previous section, like the one where we looked at the graph of x squared, and we were looking at the slope of the tan line as x approached 1. And then we looked at the slope of the tan line, right, and we did the calculations. We had a little function that we came up with from our slope formula. And so we plugged in values of x that were getting closer and closer to 1 to see what happened to the values of our slope formula, right? So in that case, our a value was 1 because we were looking at values of x that were getting closer and closer to 1. And then the slope formula that we developed was our function f of x. Now this L value, that's the value of the function. Right? That's a y value. So if you always want to keep that in mind, this a value, we call it, is an x value, and the L value is a y value. Right? And so you're plugging in values of x that are getting closer and closer to this a value, and we want to see what the function values are as we plug in those values for x. Right? And if the function values are getting closer and closer to some number, and that's what we saw in those examples, in the example previously, then that's your L value, that's your limit, right? So then we say that the limit of f of x as x approaches a is L. Now we're going to have a lot more discussion about that definition, and that's the basic notation. And remember I told you before, the notation, the terminology, the language, we have to be clear on that, but we're going to get a lot more in depth with exactly what that statement means. Right? So again, we're just scratching the surface at this point. Now, watch your language here again. Right? So some of the wording that's used, and again, we'll kind of clarify and talk a little bit about this. If we can make the value of f of x arbitrarily close to L by taking x to be sufficiently close to a on either side of a, but not equal to a, then we could say that f of x approaches L as x approaches a. So notice the use of these terms like, because like I said, we want to plug in values of x that are getting closer and closer to our a value. Or how close do we have to get? That's a logical question to ask, and we're going to address that in more detail later. But for now, it's sufficient to say, well, I want to plug in the values of x that are getting close to that a value until I can make an observation about what happens to the values of the function. And I think we had a little discussion on that in the previous section. We said, okay, we're going to plug in values for x that are getting closer and closer to 1. How close do I need to get to 1? Well, you have to plug in values that are getting closer and closer to your a value until it is absolutely clear, or at least you can make a reasonable observation about what's happening to your function values. And I could say, okay, I can go ahead and plug in numbers closer and closer to my A value from this point forward, but it's not going to change my observation. I can already tell you that my function values are approaching a specific number. That's so the use of this term arbitrarily close to L, right? So we want to make the values of f of x, we want to make our y values arbitrarily close to whatever that limit number happens to be by taking x to be sufficiently close to a. So we say, well, how close do we have to be? Well, it has to be sufficiently close enough to where we can tell you what that limit is. And it doesn't matter if I plug in numbers that are closer to a from this point forward, it's not going to change the observation about that limit value. And so again, we're going to have a lot more discussion on this. If that doesn't seem very clear, right, that's as vague as we can be at this point. It's going to become clearer later, but we need more tools before we can get into the real in-depth, discussion of exactly what all this means. Now, we did mention before, right, you do want to plug in values on either side of a. And we say when you're looking to see what the behavior of the function is, you always want to look at what's happening on both sides of your a values. So remember, we plugged in numbers from the left, we plugged in numbers from the right, and we wanted to see what the behavior was coming from both sides. Because as we're going to start to see now, you may not necessarily get the same behavior. Right? So we want to look and see what happens on both sides so we can make an accurate observation. But not equal to a. And I'm fixing to make a statement to that effect. And so I want to look at what's happening as, remember, we're interested in what's happening as x approaches a. I don't care what happens at x equals a, right? So I don't bother, I don't want to plug a into this thing, at least not yet. We'll have, again, discussion more on that. But in the evaluation of a limit, ultimately it's about the observation of what is the function doing as you approach the a value, not what's happening at the a value, right? So then we can make that observation. We can say that f of x approaches L as x approaches a, if we can see that pattern. So yeah, if the function, or in finding the limit as x approaches a of f of x, we never consider x equals a. Right, so this is what I was saying earlier, right? So it's all about what is happening as you're approaching a. F of x doesn't even need to be defined at x equals a. And I don't even have to have my function defined, or a doesn't even have to be in the domain of our function. It's all about what's happening to the value of the function as you're approaching or getting near that a value, right? I don't care what's happening at that point. A few little graphical examples. And notice in each of these three examples, I have basically the same graph. A couple little variations. So to say that f of x approaches L as x approaches a. So notice in the first case, and this is pretty obvious, like I said, being clear, being, on the notation and the terminology. So here's my function traveling along, blah, 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 blah. Here's my a value. So as we're approaching a from the left side, right, we're approaching a from here, my function values are getting closer and closer to this L value. That's my y value. And notice also as we approach from this side, right, as we approach a from the right side, I have a function or a graph that's approaching this same point. So graphically, and keep that in mind too, when you're evaluating or trying to find the value of a limit, you can always graph the function and make a visual observation on what it appears, what the limit appears to be, if there is one. Right, so don't forget that. I mean, we're going to look at all these processes manually, for evaluating limits and doing calculations and so forth. But you always can use the graph kind of as a backup. It's not going to be sufficient for our purposes because we want to actually focus on the processes that we use to evaluate limits. Because what if the graph isn't clear? What if it's not an easy graph to observe or even an easy function to graph? I want to be able to evaluate that limit without having to look at the graph. But, use that to your advantage. You can always graph the function and visually inspect what's happening to the y values, right? What's happening to the function values as your x values approach that specific a value, right? So in this case, as we approach the a, as we move left and right along our graph, our function value is approaching that same y value. That's our L value. That would be our limit. Notice in the second one, The difference here being at a, this function is undefined, right? There's a hole in the graph here, so a is not in the domain of that function. There's no point on my graph. But that doesn't change the limit, because as we approach this point from the left, and as we approach this point from the right, the graph is still approaching the same point, right? The y values are still getting close to that L value, whatever that happens to be. Okay, so that's what we said. It doesn't even have to be defined there. Now notice in that third one, right, there's again the graph with the hole. So there's a hole in the graph there. But I've changed it to where now this function is defined. There's f of a. It's that value, it's that y value. But again, that doesn't change the value of our limit. Because as this graph, as this function is approaching, as x approaches a, I should say, from the left and from the right, those y values, the graph of that function is still approaching this same L value right there. The fact that there's a point on the graph down here doesn't mean a thing. Now that's the value of our function when x equals a. All right. But like we keep saying, we don't care about what happens at a. When you're evaluating a limit, it's all about what happens as you're approaching a, or as you get close to a. And as straightforward as a concept as that may appear, I know that gives students issues sometimes, right? Because like I said, we're looking at the limit. It's all in the statement as x approaches a. All right. So please keep that in mind. That's always an issue when you're getting used to this concept. So what I want to do for the next few examples, just giving you some different ideas or different observations as far as the things that can happen when you're evaluating a limit. All right, at this point, what we're doing is just doing the calculations like we did previously, in that I'm looking at the value of this function, in this case, finding the value of the limit as x approaches -1 of that function x squared minus 1 over x plus 1. And so I want to see what happens to the value of that function as x approaches -1. And notice in this case, right, -1 is not in the domain of that function. If I plug -1 into that function, I have an undefined fraction. So f of -1 is undefined in this case. But again, like we said, we don't really care whether it's defined or not. We're interested in what happens as we approach that point, as x approaches -1. So similar to what we had done in the previous section, just made a table of values, right? And we're going to let x approach -1 from the left and from the right. Like I said, when you're evaluating a limit, you always want to plug in values from the left and from the right of your number and see what kind of observation we can make. Now I want to show you a quick way to do this on your calculator. Right, because what we're doing is we're plugging in -0.9, -0.99, -0.999. All of those values are getting plugged into our function x squared minus 1 over x plus 1. So I don't want you to have to spend a bunch of time doing all these calculations and typing all this stuff into your calculator. So here's maybe a streamlined way to do it. And some of you may be familiar with this because I showed y'all in, if you took algebra with me, I know I show you how to do this in algebra. But if you're not familiar with this process, then this will definitely save you a bunch of time when you're plugging in a lot of values into the same function, especially. So the first thing you're going to do is go to your second window. And if you hit second window on your calculator, notice that says table set. That is, let me change my, so I'm trying to get here, second window, table set. And it pulls up this little menu that allows you to make some changes to the settings on your table of values. All right, the first thing says table start. Right, I don't care about that. Whatever that number is, is when you pull up the table on your calculator. That's the first x value that you would see. I don't care about that. The next little statement is delta table. That's the Greek letter delta. We're actually going to talk about this guy a bit later. That's going to come up in our discussion as part of calculus. It is a symbol that we do use. But it's the Greek letter delta, capital letter delta. We're actually going to use the lowercase delta as well. But we use that in math to represent change. So when you see that little triangle, that's delta table, that means the change in the table. So that's set to 1, which means when you pull up your table of values, your x's are going to increment or count by 1. And you can set that to any number. You can set them to count by 5, 10, you could even do decimals, whatever. But again, I don't care about that. What I do care about is the next one. You have independent and dependent. Get this out of our way. All right. The independent, remember from algebra, your independent variable, that's your input variable. That's your x. Your dependent variable, that's your output variable. That's your y. Right? We want the x to be set to auto so that I can manually plug in whatever values I want to into my function. So set your independent to auto and leave your dependent, set your independent to ask, keep saying auto, and leave your dependent on auto. And that way, then when you pull up your table of values, when you hit second graph, right, to get to your table will allow you to enter in these different x values into our function. Right? Now, we do also want to go ahead and put our function into our y equals. Right? So whatever the function is that we're evaluating, put that into your y equals editor. So in this case, it's x squared minus 1 over x plus 1. So I'm going to go ahead and put that into y equals. Also, as a reminder, because I know this happens if you use your calculator to do statistics and that type of thing, we end up turning these plots on. Make sure your plots are off. If any of those are highlighted and you do a graph or manipulate these functions, you're probably going to get an error when you do that. So make sure your plots are turned off. If any of those are highlighted, just hit your up arrow until it's highlighted and hit enter and it'll turn it off. Because I know that happens sometimes. We get errors. So make sure your stat plots are turned off. But go ahead and enter your function into your y equals. And then go to your table and hit second graph. And depending on if you've used this before, you may or may not have values in the table when you do this. Right? So if you've used this feature before, you're going to see some numbers there already. I went ahead and cleared mine out. Now you can clear out those numbers. You have to do them manually. You highlight the X and you hit the clear button and hit enter, and then it'll delete each of those, but you have to do them manually. That's the quickest way I've found to do it. But irrelevant. I mean, I can have numbers there. It doesn't change anything. But now what you're going to do from this point forward is simply type in the numbers that you want in place of X. Right, so on our chart, since we're using like negative 0.9, negative 0.99, etc., negative 0.1, 1.1, 1.01, and so forth, you're just going to type those in. Right? So just type in negative 0.9, hit enter. Type in negative 0.99, hit enter, and so forth. And you can quickly plug in each of those numbers, and there are your y values. Right? And so that's what we're interested in. So x approaches a in this case is negative 1. So we're plugging in values from the left and from the right of negative 1. And then we're looking at what happens to those y values. Those are our function values. Right? And then we're looking to see if those are approaching or getting close to some number. And in this case, right, from both sides, right, from the left and from the right, go back to a dark color, we can see that the function values are approaching negative 2. Right? These guys are getting close to negative 2, and these guys are getting close to negative 2. Right? So we can make the observation then, again, keep that in mind, this is still just an observation that we are making based upon the values that we see in our table. Right? So we can make the observation and say that it looks like f of x is approaching negative 2 as x approaches negative 1. Or in terms of our limit statement, we could say that the limit as x approaches 1 of as x approaches negative 1, of x squared minus 1 over x plus 1 equals negative 2. All right? But the bottom line is, what are we trying to observe? We want to see what the function values are doing. What are the y values doing as you plug in x values that are getting closer and closer to your a value into that function? And can we make an observation about what's happening? So these next few examples are just going to show you some different things that can happen, how we recognize it, how we describe it. So number 2, Here I'm estimating the value of the limit as t approaches 0 of that expression, square root of t squared plus 9 minus 3 over t squared. Notice again, I do have a function that is undefined at our a value. Our a value in this case is 0 as t approaches 0. So we do have a function that's undefined at 0 at our a value. But again, we don't care. Right? It's all about what happens as our t values in this case approach 0. So we're going to let t approach 0 from the left and from the right. So I'm taking values close to 0 from the right, 0.1, 0.001, 0.001, right? They're getting smaller and smaller and smaller, closer to 0. And then from the left, negative 0.01, negative 0.1, negative 0.01, negative 0.001. And so again, just like with the previous example, you could put this function into your y equals editor, and then go to your table and type in those values that are getting closer and closer to 0. Okay. Now, of course, they don't always come out to be nice, pretty numbers. Okay. But we try to make the best observation that we can based upon the information that we have. And in this case, it appears that those values are approaching 0.16 repeating. And now, I think I'd mentioned to you in the previous section, and from our discussion earlier, right? We need to make sure that we can make a clear observation as far as what these y values are doing, right? So that was that arbitrarily and sufficiently close idea from our definition earlier. So I need to plug in values for x, or in this case, values for t, until I can clearly make an observation as far as what the function values are doing. Right? And if it still wasn't clear, then I would have to go further. I would have to go say 0.0001, right? Or 0.0001, or however many zeros you need to plug into that thing, until you can make a clear observation. So we're able to at least make the observation and look at it. Looks like it appears that this function is approaching 0.16 repeating as t approaches 0. Now, I also threw in the fraction 1/6. I mean, I don't expect you to recognize that 0.16 repeating is the fraction 1/6. If you do, great. If not, no big deal. This is sufficient. We're still just estimating or approximating the value of this limit to the best of our ability. Now, if you're going into Calc 2, we're actually going to talk about how to convert a repeating decimal to a fraction. It actually takes calculus to do that, as simple as that may seem. But that'll be a discussion for Calc 2 if you're heading into that course. Number 3, let's look at or evaluate the limit as x approaches 0 of 2x squared over x minus 3. Now notice in this case, this function is defined for x equals 0. I can plug 0 into that function and I get a value. It's not undefined where x equals 0. But again, in evaluation of the limit, I don't care whether it's undefined or not. Okay? It's all about what happens as x approaches 0. What are the function values doing? And the reason I wanted to show you this one, if you plug this into your calculator, so go ahead and put the 2x squared over x minus 3 into your y equals editor. And then you go to your table. Now notice here I started with 0.01, 0.001, because I wanted to show you what happens here. And those are the values that you're going to get, or something similar. You may not get the negative 7, maybe you get the negative 6 point something something e negative 5. So my first question is, what does this mean? All right. That's scientific notation. Remember scientific notation? To say, and this is how the calculator shows scientific notation. So negative 7e negative 5 means negative 7 times 10 to the negative 5th power. That's what that means. Remember that scientific notation? And anytime you have this negative exponent on the 10, what does that represent? Well, that represents a really small number. All right, it means that there's going to be 5 decimal places here. So in other words, it's negative 0.1234, 5. All right. So that's the number represented by negative 7e negative 5. And then the next one is negative 7e negative 7. Well, what does that mean? Well, I'm just going to have to add a couple more decimal places here. So I get negative 7.1, 2, 3, 4, 5, 6, 7. All right. So what's happening is these numbers are getting smaller and smaller and smaller, right? Negative 70, negative 9. I'm just going to throw in a couple more zeros, right? So anytime you see a number like this popping up, this is a number that's really, really small when you have scientific notations with exponents on the 10 of negative numbers. And they're getting smaller and smaller and smaller, right? So if we continue to plug in 0.00001 and so forth, you're just going to see those numbers continue to get smaller and smaller and smaller. In other words, they're approaching zero. All right, so that's the observation I want to get out of this one when you see things like that. Now, for clarification, I want to say this, and we'll probably remind you again later. Thinking about values in general, some of the terms we use, we don't want a misunderstanding or miscommunication on what we mean. When I say a number is getting small, I mean that number is getting close to zero. Right? As opposed to, when you go on a number line, and we have zero here, we have our negative numbers here, positive numbers there. When you're talking about a number line, as you move to the left on a number line, your numbers are getting smaller, right? They get small as you move to the left, and they get larger as you move to the right. But I don't want miscommunication or misunderstanding here. When we use the term small to describe a value, we are talking about numbers that are getting close to zero. Maybe they're small positive numbers, small negative numbers, but they're getting close to zero. If I want to describe a number that's going out this way, we're going to describe that by saying it's getting larger negative. So I can get larger negative if I'm moving to the left on the number line. I can get larger positive if we're moving to the right. And if I have a number that's approaching zero, that's what we describe as a small number, or a number that is getting smaller, right? Because you can misinterpret that. Technically, we always say on a number line, you move to the left, you get smaller, you move to the right, you get larger. But we want to be clear as far as the difference between what we're describing. So we always say large negative or large positive, and then small means we're getting close to zero. So in this case, and then, we'll finish this up. So notice on the other side, if we approach zero from the left, plugging in the negative 0.01, 0.01, etc., again, we get numbers similar to what we got on the other side, right? But in either case, they are approaching zero. So we can make the observation that it looks like the limit as x approaches zero of that expression is zero. Now here's the same function, but in this case, we're going to look at what's happening as x approaches 3. Because notice that function is undefined, where x equals 3. All right, so what's the behavior of the function? What's happening to our function values as x approaches that point at which the function is undefined? Notice it's kind of a common theme. We keep looking at a lot of these limits as we approach a point on the graph of our function, or in the function where the function is undefined. Right? And so we're trying to describe the behavior of that function. So look at what happens in this case. So here I'm plugging in numbers to the right of 3, 3.01, 3.001, and so forth. And look what's happening to our function values. 1812, 18,012, 180,012, and then a decimal tacked onto that. But what's happening is those numbers are getting larger. Right? And specifically, I would say in this case that they are getting large positive, right? Because we want to be very clear when we're describing these behaviors. We don't want misinterpretation. So these values are getting larger positive, or we could say that looks like they're approaching positive infinity. Right? So if I just plug in numbers that are getting closer and closer to 3, plug in 3.00001, then you're going to see a number that's going to continue to grow in value. Same thing happens on the other side of 3, but instead of our numbers approaching positive infinity, these are getting larger negative, right? So we plug in 2.9, 2.99, and 2.999, etc. And I'm getting these values that are getting larger, but they're getting larger negative, right? So I would say that this behavior is the value of the function. F of x is approaching negative infinity as x approaches 3 from the left side, okay? And so again, this is why we always say you want to look at what's happening from both sides of your number. You may get the same behavior. It may be approaching the same point, or it may be different. So now, in terms of the limit itself, to say that a limit exists would mean that this or that these function values would have to be approaching the same number from the left and from the right, like we've had in each of the previous examples. But in this case, two different things to mention here. First of all, notice that the function values are not approaching a number. Right? The fact that they're either approaching positive infinity or negative infinity means that they're either getting large positive or large negative without bound. They are not approaching a single number. So in that sense, we would say that the limit does not exist. In order for a limit to exist, it must approach a specific value. Right? And if it doesn't, then the limit does not exist, because that's what you're describing. You're saying that the function values are approaching a specific number or a specific value as your x value approaches the a value. So in this case, the limit does not exist because it does not approach a specific value. The other thing, notice it's two different behaviors on both sides. Right? As we approach 3 from the right, that first group of values, we're getting large positive. As we approach 3 from the left, the second group, we're getting large negative. Right? So we have a different behavior on either side. Right? So that's another issue with whether or not the limit exists that we'll be discussing going forward. So we'll say that this number does not approach one value or a single value as x approaches 3 from the left and from the right, and that's one of the ways that we can then say that this limit does not exist. So again, we'll talk more about that going forward, but that's another possible behavior. Now, the behavior of the function on the both of the different sides, as we approach 3 from the left, as we approach 3 from the right, in that previous example, we had two different behaviors. And we always said, or we keep saying, that we want to evaluate the limit by looking at what happens from both sides. Well, in some cases, we're only going to be interested in what happens on one side. Or maybe if the behavior is different on both sides of the a value, we can describe what happens on each side individually, right? Using what we'll call a one-sided limit. And so instead of just talking about the limit as x approaches a of f of x, let's look at the limit as x approaches a from the left of f of x. Or look at the limit as x approaches a from the right of f of x. So our left-hand limit, we'll call it, the limit as x approaches a from the left of f of x equals L, where here we're only considering values of x that are less than our a value, right? So we're approaching a from the left, we're only going to look at values of x that are smaller or less than the a value. And then conversely, on the right side, the limit as x approaches a from the right, call that our right-hand limit, and we're only considering values of x that are larger than a or to the right of a. Right? So there's notation there. Now, again, you want to be very clear with your notation. So we're talking about three different limits now. We're talking about the left-hand limit, the right-hand limit, and then the overall limit. Right? The limit as x approaches a of f of x. This next statement right here, this is a big deal. I've got 3 stars over here, so it must be pretty important. So always keep this in mind when you are evaluating a limit. To say that the limit as x approaches a of f of x equals L, this is true if and only if. That's an if statement with 2 f's. It's not an if, it's if and only if. So that's a powerful if statement. So in other words, this happens only if the following statement is true. And so therefore, if the following statement is not true, then our original statement cannot be true. So that limit as x approaches a of f of x equals L if and only if the left-hand limit, the limit as x approaches a from the left of f of x equals L, and the right-hand limit, the limit as x approaches a from the right of f of x equals L. So this is going to give us another way that we can determine the value of a limit. In some cases, it may not be possible, or it may not be easy to look at just the overall limit as x approaches a. We may have to use an observation about the left-hand limit and the right-hand limit. And if I can look at the left-hand limit, evaluate that limit and get a value for L, and evaluate the right-hand limit, get a value for L, if those are the same, then I can say the overall limit exists. If they're not the same, then it doesn't. Right? So bottom line, that's and it's a powerful statement. It's a pretty important statement, and it gets overlooked a lot, right, in evaluating limits. But we're going to harp on that extensively, because that's always a go back to, if I'm trying to evaluate a limit, if I can't do it directly, well, let's look at the left-hand limit, let's look at the right-hand limit. And if I can show that those are the same, then I can tell you that our limit exists. So for example, this is going to be a graphical example. Right, so we're going to obviously deal with a lot of the calculation part of things, and do the manual evaluation of the limits. But like I said before, make use of the graph. Right? Do a graphical observation. You can always use that to back up your observation or your calculations that you're making. But I also want to show you what happens graphically, because I think understanding the graphical nature of this goes a long way as well into understanding what we mean by the evaluation of a limit or the existence of a limit. So, and I have the diagram here on the right. So I'm looking at graphically evaluating each of these limits. So look at part A, part B, part C. I'm looking at the limit as x approaches 2 from the left of g of x, the limit as x approaches 2 from the right of g of x, and then the limit as x approaches 2 of this function g of x. Right? So I'm looking at the behavior of this function as x approaches 2. Right? That's our a value in the context of our limit definition. Right? The limit as x approaches a. And as we approach 2 from the left, that means I'm coming in from this left side. Right? Just follow the graph from the left. That's all that you have to do with this. Right? Nothing more to it than that, to say that I'm looking at what happens to f of x, or in this case g of x, as x approaches a, or in this case as x approaches 2, what happens to the function values as we approach from the left side of that number. And our function values are approaching this point. Right? As I come in from this left side, my graph is approaching 3. As we approach 2 from the right side, it's okay, what's the limit as x approaches 2 from the right side? Well, as we approach 2 from the right, our function values are approaching 1. Right? So there's our left-hand and right-hand limits. The limit as x approaches 2 from the left of f of x equals 3. The limit as x approaches 2 from the right of g of x equals 1. And then from our previous statement, what is the limit as x approaches 2 of g of x? Well, I would say that that limit does not exist. Why? Because the graph, the function values approach 2 different numbers. As we approach 2 from the left, we're approaching 1 point. As we approach 2 from the right, we're approaching a different point, or a different value. And so that's one way that we can evaluate the overall limit. I could say that the left-hand limit and the right-hand limit are not the same. Therefore, the limit as x approaches 2 of g of x does not exist. Okay? And also notice graphically, this is one way you can tell from a graph whether your limit exists as you approach a specific point. Notice there's a big gap in the graph. Right? Obviously, the two sides of the graph are approaching 2 different points. Okay? So since they're not approaching the same point, the limit does not exist. Now, the other one we're looking at is what happens as x approaches 5. So limit as x approaches 5 from the left of g of x, from the right of g of x, and then the overall limit as x approaches 5 of g of x. So parts D, E, and F. So that's the other place we have some kind of stuff happening on our graph. So again, here's our a value, our new a value, 5 in this case. And so as x approaches 5 from the left, right, as we move toward that point from the left side, our graph is approaching 2. It's approaching this point, which is 2. And as x approaches 5 from the right, we're approaching the same value, right? We're approaching 2. Now notice there is a point on the graph right here. That's the value of f of 5. Right? F of 5 equals 1, according to this graph. But we said when we were evaluating a limit, I don't care what happens at our a value. I don't care what happens at x equals 5. It's all about what's happening as x approaches 5. So the limit as x approaches 5 from the left is 2. The limit as x approaches 5 from the right is 2. And since the left-hand limit and the right-hand limit both approach the same value, then we can say that the overall limit as x approaches 5 of g of x is 2. And then I've also made that note that notice g of 5 is not equal to 2. G of 5 equals 1. Right? That's where that point is that we have here. So there's our function value. There's g of 5. It's equal to 1. But it's not the same as the limit. Right? I don't care. Right? When we're evaluating a limit, it's all about what happens as we approach that point, or as we approach that particular x value, our a value. I don't care what happens at that point. Now, that's going to make a difference for something else that we're going to talk about, but in terms of the limit, I don't care. Here's another possible behavior, right? So in all of the previous examples, well, I say all of them, actually one of them we did have this happen, but in most of the examples, we actually had the value of the function or the function approaching a specific point. Okay? Maybe it wasn't the same from both sides, but they were approaching specific values. We did have that earlier example, and this is the continuation of that. Well, what happens if the value of the function is getting larger, positive, or larger negative? And we had that example earlier where one side, as we approached 3, I think it was, right, the value of the function got larger, positive, it was approaching infinity, and we approached from the other side, it was approaching negative infinity. So that's what we call an infinite limit, right? So definition, let f be a function defined on both sides of a, except possibly at a itself. You're always going to see that statement, right, when we're talking about limit definitions, because like we said, we're approaching from both sides of a. We don't care what happens at a itself. It's all about what happens as we approach it. So you're going to typically see that in a lot of these definitions involving the existence of limits. Right? So let f be a function defined on both sides of a except possibly at a. Then the limit as x approaches a of f of x equals infinity means that the value of f of x can be made arbitrarily large by taking x sufficiently close to a. All right, so similar to that definition that we had before with the arbitrarily and sufficiently. We want the x values sufficiently close to a. We want to get as close as we need to be able to make the observation that the values of the function are just going to continue to get large. Right? Whether they're large positive, and it's going to be a similar definition for negative infinity. But for example, right, and I think, that the definition sometimes can be a little, you have to kind of let that digest in your mind. The observation, I think, is pretty straightforward, right? But so we have to tie the wording into the observation, or the visual observation that we can make. So consider, say, for example, the function f of x equals 1 over x squared. And we have a function that's undefined where x equals 0 in this case. If you look at that limit as x approaches 0 of 1 over x squared, right, graphically we can make the observation that, look, the graph of that function is shooting off to infinity. Right? The values are getting larger and larger. And we talk about this is a rational function. There's a vertical asymptote here. Right? The y-axis in this case is a vertical asymptote, because as x approaches 0, the graph of that function is just going to continue to shoot off to infinity. It's going to get closer and closer and closer to that y-axis without ever touching it. It can't touch it because 0 is not in the domain of our function. And so we're going to mention vertical asymptotes. There obviously is some type of relationship there. Now, this does not mean that we are treating infinity as a number. You never, ever, ever treat infinity as a number. Remember, infinity is used to describe a behavior. Right? We're able to describe, or we're able to say that the values of this function are getting larger, large positive in this case, as x approaches 0. But that's all infinity is used to describe. Right? So like we said before, this limit does not exist. Right? It does not exist because the value of the function is not approaching a specific number. Right? The fact that it's approaching infinity simply means that it's getting larger and larger and larger. All right, so we're describing the behavior of the function. We would still say here that this limit does not exist, but we are at least able to describe the behavior. So we do that whenever possible. So if I'm given a question that says, what is the limit as x approaches 0 of 1 over x squared, I would say that that limit is infinity, right? Even though technically it does not exist, I'm still able to describe the behavior, right? But do keep that in mind, right? Anytime we use this or have this type of observation. Yeah, so I'm going to go ahead and mention this while I'm thinking about it. When you look at a function like this, like 1 over x squared, notice the values of x are getting closer and closer to 0. So if I have a fixed numerator, in this case my numerator is 1, and the denominator contains a variable, as the value of that denominator approaches 0 or gets smaller, notice what's happening to the value of the fraction. The fraction is getting larger. All right, so we're saying that as x approaches 0, the denominator is approaching 0, it's getting smaller. The value of the fraction, 1 over x squared, is getting larger. It's approaching infinity. That's an important little observation to make. So there's kind of an inverse relationship there between what's happening with the value of the denominator and what happens to the value of the fraction. So that's something we're going to see pop up. We're going to mention that. So kind of keep that observation in mind. All right, similarly, as we said, the limit as x approaches f of x equals negative infinity. It means basically the same thing, right? But instead of our values getting larger positive, they're going to get larger negative. So if f of x can be made arbitrarily large negative, and this is what I had mentioned earlier, we want to make sure we're clear on that. So we're saying that the values of the function are getting large positive or large negative, right? In this case, large negative by taking x sufficiently close to a, but not equal to a, right? Because we never consider x equal to a when we're evaluating a limit. Then we could say that the limit as x approaches 0, in this case of, say, negative 1 over x squared, is negative infinity, right? Because we do have the graph in this case shooting off towards negative infinity as x approaches 0. Just to touch base back with that one we did talk about, kind of ties in a couple of different things that we've mentioned. That example that we had earlier, the f of x equals 2x squared over x minus 3, that was the one that we said if you looked at the limit as x approaches 3 of f of x, it did not exist because as you approached 3 from one side, the left side in this case, the values got large negative, right? So we're able now, just kind of tying this into the idea of one-sided limits, so the limit as x approaches 3 of f of x does not exist, period. And there's nothing else that I can do to describe that. We could, though, describe each of those one-sided limits. The limit as x approaches 3 from the left of f of x equals negative infinity, and you can go back and look at the chart that we had for that particular example. And the limit as x approaches 3 from the right of f of x equals infinity. Now again, those two limits still do not exist, right? But at least we are able to describe the behavior of the function as x approaches 3. And lastly, so this is going to tie in the observation we made about that vertical asymptote in the previous example with 1 over x squared. And the same thing would be true with this function, 2x squared over x minus 3. We now have call it a calculus definition for the existence of a vertical asymptote. So if my question is identify or find the vertical asymptotes on the graph of our function, this is how we would have to do it. We would have to justify the existence of a vertical asymptote using our limit definition. Now it's a vertical asymptote, so it is a vertical line. Remember vertical lines. X equals a number. So I would say that the line x equals a is called a vertical asymptote of our curve or of our function y equals f of x if at least one of the following statements is true. And that all has to do with these infinite limits. If the limit as x approaches a of f of x equals infinity, the limit as x approaches a of f of x equals negative infinity, or one of those one-sided limits, right, as x approaches a from the left or the right. So bottom line is, if you're evaluating a limit, and that limit is either approaching infinity or negative infinity, from either one side or both, then that gives me the existence, or shows me the existence, of a vertical asymptote, whose equation would be x equals a, right? Whatever that value is that you're approaching, okay? So in this case, that's how I would justify that. I could tell you that, look, on the graph of this function, 2x squared over x minus 3, I know there's a vertical asymptote at x equals 3. How do I know that? Because the limit as x approaches 3 from the left equals negative infinity. I could also justify it by saying the limit as x approaches 3 from the right equals infinity. So notice it doesn't have to be the same. Okay? So if you were to graph this function, you can pull this up on your calculator. We know there's a vertical asymptote right here at 3. And let's see, we have there is no horizontal asymptote, but that at least would show me that the behavior as x approaches 3 from the left of this function would be this. Oop, wrong way. X approaches 3 from the left, it's approaching negative infinity. And as x approaches 3 from the right, it's approaching infinity. So whatever the rest of the graph of that function looks like, I know that that's the behavior of that graph as x approaches 3. Right? And so these are the types of things that we're going to continue to talk about going forward, and we can get information about what the graph of a function looks like just based upon these observations. And at some point, we're going to put all that together to help us sketch graphs and so forth. So that'll be it for this section.